Learning objectives. In this chapter, the user will learn the following in detail. Data mining issues in object-oriented databases, spatial databases and multimedia databases, time series databases, text databases, web mining, web usage mining, web content mining, web log attribute. Data mining issues in object-oriented databases. Data mining issues. Data mining is not an easy task as the algorithms used can get very complex and data is not always available at one place. It needs to be integrated from various heterogeneous data sources. These factors also create some issues. Let us discuss the major issues regarding mining methodology and user interaction, performance issues, diverse data type issues, data mining issues are represented here. Mining methodology and user interaction issues. It refers to the following kinds of issues. Mining different kinds of knowledge in databases. Different users may be interested in different kinds of knowledge. Therefore, it is necessary for data mining to cover a broad range of knowledge discovery tasks. Interactive mining of knowledge at multiple levels of abstraction. The data mining process needs to be interactive because it allows users to focus the search for patterns, providing and refining data mining requests based on the returned results. Incorporation of background knowledge. To guide discovery process and to express the discovered patterns, the background knowledge can be used. Background knowledge may be used to express the discovered patterns, not only in concise terms, but at multiple levels of abstraction. Data mining query languages and ad hoc data mining. Data mining query language that allows the user to describe ad hoc mining tasks should be integrated with the data warehouse query language and optimized for efficient and flexible data mining. Presentation and visualization of data mining results. Once the patterns are discovered, it needs to be expressed in high-level languages and visual representations. These representations should be easily understandable. Handling noisy or incomplete data. The data cleaning methods are required to handle the noise and incomplete objects while mining the data regularities. If the data cleaning methods are not there, then the accuracy of the discovered patterns will be poor. Pattern evaluation. The patterns discovered should be interesting because either they represent common knowledge or lack novelty. Performance issues. There can be performance-related issues such as follows. Efficiency and scalability of data mining algorithms. In order to effectively extract the information from huge amount of data in databases, data mining algorithm must be efficient and scalable. Parallel, distributed and incremental mining algorithms. The factors such as huge size of databases, wide distribution of data, and complexity of data mining methods motivate the development of parallel and distributed data mining algorithms. These algorithms divide the data into partitions, which is further processed in a parallel fashion. Then the results from the partitions are merged. The incremental algorithms update databases without mining the data again from scratch. Diverse data types issues. Handling of relational and complex types of data. The database may contain complex data objects, multimedia data objects, spatial data, temporal data, etc. It is not possible for one system to mine all these kind of data. Mining information from heterogeneous databases and global information systems. The data is available at different data sources on LAN or WAN. These data sources may be structured, semi-structured, or unstructured. Therefore, mining the knowledge from them adds challenges to data mining. Other issues in data mining. Security and social issues. Security is an important issue with any data collection that is shared and/or is intended to be used for strategic decision making. When data is collected for customer profiling, user behavior understanding, correlating personal data with other information, etc., large amounts of sensitive and private information about individuals or companies are gathered and stored. This becomes controversial given the confidential nature of some of this data and the potential illegal access to the information. Data mining could disclose new implicit knowledge about individuals or groups that could be against privacy policies, especially if there is a potential dissemination of discovered information. Another issue that arises from this concern is the appropriate use of data mining. Due to the value of data, databases of all sorts of content are regularly sold, and because of the competitive advantage that can be attained from implicit knowledge discovered, some important information could be withheld, while other information could be widely distributed and used without control. User interface issues. The knowledge discovered by data mining tools is useful as long as it is interesting and above all understandable by the user. Good data visualization eases the interpretation of data mining results as well as helping users better understand their needs. Many data exploratory analysis tasks are significantly facilitated by the ability to see data in an appropriate visual presentation. There are many visualization ideas and proposals for effective data graphical presentation. However, there is still much research to accomplish in order to obtain good visualization tools for large data sets that could be used to display and manipulate mined knowledge. The major issues related to user interfaces and visualization are screen real estate, information rendering, and interaction. Interactivity with the data and data mining results is crucial since it provides means for the user to focus and refine the mining tasks as well as to picture the discovered knowledge from different angles and at different conceptual levels. Mining methodology issues. These issues pertain to the data mining approaches applied and their limitations. Topics such as versatility of the mining approaches, the diversity of data available, the dimensionality of the domain, the broad analysis needs when known, the assessment of the knowledge discovered, the exploitation of background knowledge and metadata, the control and handling of noise and data, etc., are all examples that can dictate mining methodology choices. For instance, it is often desirable to have different data mining methods available, since different approaches may perform differently depending upon the data at hand. Performance issues. Many artificial intelligence and statistical methods exist for data analysis and interpretation. Terabyte sizes are common. This raises the issue of scalability and efficiency of the data mining methods when processing considerably large data. Algorithms with exponential and even medium-order polynomial complexity cannot be of practical use for data mining. Linear algorithms are usually the norm. In the same theme, sampling can be used for mining instead of the whole data set. However, concerns such as completeness and choice of samples may arise. Other topics in the use of performance are incremental updating and parallel programming. There is no doubt that parallelism can help solve the size problem if the dataset can be subdivided and the results can be merged later. Incremental updating is important for merging results from parallel mining or updating data mining results when new data becomes available without having to reanalyze the complete dataset. Data source issues. Regarding the practical issues related to data sources, there is the subject of heterogeneous databases and the focus on diverse complex data types. We are storing different types of data in a variety of repositories. It is difficult to expect a data mining system to effectively and efficiently achieve good mining results on all kinds of data and sources. Different kinds of data and sources may require distinct algorithms and methodologies. Currently, there is a focus on relational databases and data warehouses, but other approaches need to be pioneered for other specific complex data types. A versatile data mining tool for all sorts of data may not be realistic. Moreover, the proliferation of heterogeneous data sources at structural and semantic levels poses important challenges not only to the database community but also to the data mining community. Multimedia database. Multimedia is a combination of different media, that is, text, pictures, sound, video, animations, etc., used to present multimodal information in conjunction with computer technology. A multimedia database is a collection of related multimedia data. Figure shows a multimedia system. Main task of a database management system, DBMS, is to abstract from the details of storage access, storage management, location of the MDBMS, embedded between the application domain and the device domain, integration into the system through operating system communication components, persistence of data, data outlive processing programs and technologies. For example, companies have to keep data in databases for several decades. Consistent view of data. Synchronization protocols provide a consistent view of data in a multi-user system. Security of data. Transaction concepts ensure security and integrity protection in case of system failure. Recovery of lost data. Query and retrieval of data. Query languages such as SQL, structured query language, enable formulating database queries. Each entry has its state information that can be retrieved correctly. Common multimedia data types that can be found in a multimedia database include the following: text, graphics, drawings, sketches and illustrations, images, color and black and white pictures, photographs, maps and paintings, animation sequences, animated images or graphic objects, video, a sequence of images, frames, typically recording a real-life event and usually produced by a video recorder. Audio, generated from an oral recording device. Composite multimedia, a combination of two or more of the above data types. Characteristics of multimedia data. Lack of structure. Multimedia data often are not quite structured. Therefore, standard indexing and content-based search and retrieval may not be available. Temporality. Different multimedia data types have different requirements. For example, some multimedia data types such as video, audio, and animation sequences have temporal requirements that have implications on their storage, manipulation, and presentation, but images, video, and graphics data have spatial constraints in terms of their content. Massive volume. Usually the data size of multimedia is large, such as video. Therefore, multimedia data often require a large storage device. Logistics. Non-standard media can complicate processing. For example, a multimedia database application requires using compression algorithms. Characteristics of MDBMS. Corresponding storage media. Multimedia data must be stored and managed according to the specific characteristics of the available storage media. Descriptive search methods. Query of multimedia data should be based on descriptive and content-oriented search. For example, a picture of a woman with a red scarf. Device-independent interface. Hide details of device control but offer information on specific characteristics of available storage media. Read only, write once, write many. Format-independent interface. DBMS must hide internal storage format and offer conversions to formats requested by applications, GIF, JPEG, etc. This allows changing to a new storage technologies without any impact on multimedia applications. View-specific and simultaneous data access allows consistent, multiple and simultaneous data access through different queries of several applications. For example, shared editing. Management of large amounts of data. DBMS must be capable of handling and managing large amounts of data. Need of appropriate referencing mechanisms. Relational consistency of data management. Relations among data of one or different media must stay consistent corresponding to their specification. MDBMS manages the following relations. Attribute relation supports different presentation, audio, video, image of one object. Component relation includes all parts belonging to one data object. Substitution relation defines different kinds of presentation of the same information. For example, equation as tables, graphs, animation. Synchronization relation describes temporal relations between data units, that is, lip synchronization of audio and video. Real-time data transfer. DBMS must perform read and write operations of continuous data in real time. The data transfer of continuous data has a higher priority than other database management actions. Primitives of multimedia operating systems should be used to support the real-time transfer of continuous data. Long transactions. The transfer of large amounts of data will take a long time and must be done in a reliable fashion. Relation between the operating system and MDBMS. The operating system provides the management interface for MDBMS to all local devices. The MDBMS provides an abstraction of this data and their equivalent devices, as is the case in DBMS without multimedia. The communication system provides for MDBMS abstractions for communication with entities at remote computers. Operating system and communication system can unify all the different abstractions and offer them. Data structure. Data can be stored in databases as unstructured, unformatted. Data are presented in a unit where content cannot be retrieved by accessing any structural detail. Example, Mr. Penguin is a student in the 7th term. Structured form, formatted. Data are stored in variables, field or attributes with corresponding values. Example, o.student.surname, muster name, o.student.name, Herman, o.student.age, 41. Data types. Multimedia data can be stored in databases as raw, registering, and descriptive data types. Raw data represent the unformatted information content. For example, letters, pixel, values. Registering data necessary for correct interpretation and identification of the data, usually concealed in the header. For example, format description, GIF, TIFF, JPEG, ASCII, EBCDIC, etc., compressed or uncompressed data, and so on. Descriptive data, information about content and structure of the multimedia data to make use easier and faster. For example, semantic search. Data types, examples. Text. Characters represent raw data. Registering data describe the coding, for example, ASCII. Descriptive data may include information for layout and logical structuring of the text or keywords. Image. Pixels represent raw data. Registering data include the height and width of the picture. Descriptive data are individual lines, surfaces, and subjects. Video sequence. Pixel matrices represent the raw data. Registering data provides, in addition to other information, the number of images per second. Descriptive data provide a scene description. Audio sequence. The digital sample values created by a simple PC encoding represent the raw data. Registering data represent the properties of the audio coding. Descriptive data represent the content of the audio. Operations on data. An MDBMS must offer for all data types corresponding operations for archival and retrieval. The media-related operations will be handled as part of or extension of query languages, for example, SQL. Different classes of operations are needed. Input, output, modification, deletion, comparison, evaluation. Input, insert or record operation. The data will be written to the database. The raw and registering data are always needed. Descriptive data can be attached later. Output, play operation. Read the raw data from the database according to the registering data. Modification. Changing of raw registering and descriptive data. Modification can also be understood as a data conversion from one format to another. Deletion operation. Remove an entry from the database. The consistency of the data must be preserved. Comparison. Many queries to the MDBMS consist of a search and retrieval of the stored data. Queries are based on comparison information. Individual patterns in the particular medium are compared with the stored raw data. Not successful enough. Pattern matching, search in descriptive data, etc. Evaluation. Generation of the corresponding descriptive data from the raw and registering data. Integration in a database model. Design of multimedia database systems based on two different kinds of DBMS. DBMS, Extensible Relational Database Management System. Definition of additional application-dependent data types as domains for attributes. Definition of new functions to control behavior of and access to the data. Embedding new types and functions into existing DBMS. DBMS, Object-Oriented Database Management System. Different media are represented by classes whose instance variables include the data as internal state. Class hierarchy allows object relations, offers well-information navigation, and flexible presentation possibilities. Relational database model. Simplest possibility to implement a multimedia database is to use the relational database model. The attributes of different media in relational databases are defined. Attribute can specify text, audio, video. Advantage: compatibility with existing database applications. Type 1 relational model. Value of a certain attribute can be fixed over the particular set of the corresponding attribute types. For example, the frame rate of the video can be fixed. In the example, the videos from the exercise devices 1 and 2 will play at the fixed rate defined by the Type 1 specification. Type 2 relational model. A variable number of entries can be defined through the Type 2 relational model. In the example, the individual disciplines of each admitted student are identified through their admission numbers. Type 3 relational models. Additionally, an entry can simultaneously belong to several relations. In the example, a video entry of a student can be assigned to the relation athletics as well as to the relation analysis. Object-oriented database model. In object-oriented databases, classes with objects are defined. Objects can be put in relations via a class hierarchy. A semantic specialization of classes and objects can follow. For example, main class Sports Institute, subclass Athletics Swimming, objects Students. Advantage: these systems offer good information navigation and flexible presentation possibility. Disadvantage: query operations are incompletely supported. Spatial database. A spatial database system is a database system, a DBMS with additional capabilities for handling spatial data. Offers spatial data types SDTs in its data model and query language. Structure in space, for example, point, line, region. Relationships among them, L intersects R. Supports SDT in its implementation, providing at least spatial indexing, retrieving objects in particular area without scanning the whole space, efficient algorithms for spatial joins, not simply filtering the Cartesian product. Modeling. In 2D and GIS application, two basic things need to be represented. Objects in space, distinct entities arranged in space, each of which has its own geometric description. For example, cities, forests, or rivers. Single objects. Coverage field. Say something about every point in space. View is one of the thematic maps describing Example, land use or the partition of a country into district. Spatially related collection of objects. Modeling, spatial primitives for objects. Point. A point represents an object for which only its location in space, but not its extent, is relevant. For example, a city may be modeled as a point in a model describing a large geographic area. Line, actually a curve or ploy line. A line in this context is always understood as meaning a curve in space, usually represented by a polyline, a sequence of line segments. Is the best abstraction for facilities for moving through space or connections in space. Example, roads, rivers, cables for phone, electricity, etc. Region. A region is the abstraction for something having an extent in 2D space. For example, a country, a lake, or a national park. A region may have holes and may also consist of several disjoint pieces. The figure shows three basic abstractions of point, line, and region. Modeling, coverages. The two most important instances of spatially related collections of objects are partitions and networks. Partition. Set of region objects that are required to be disjoint. Adjacency or region objects with common boundaries. The adjacency relationship is of particular interest. That is, there exist often pairs of region objects with a common boundary. Partitions can be used to represent thematic maps. Example, thematic maps. Networks. A graph embedded into the plane consisting of a set of point objects, forming its nodes, and a set of line objects describing the geometry of the edges. Networks are ubiquitous in geography. For example, highways, rivers, public transport, or power supply lines. Figure shows partitions and networks. Modeling, spatial relationships. Among the operations offered by spatial algebras, spatial relationships are the most important ones. For example, they make it possible to ask for all objects in a given relationship with a query object. Example, all objects within a window. One can distinguish several classes. Topological relationships, for example, adjacent, inside, disjoint, are invariant under topological transformations like translation, scaling, rotation. Direction relationships, for example, above, below, or north of, southwest of. Metric relationships, for example, distance. 6 valid topological relationships between two simple regions: no holes connected, disjoint, in touch, equal, cover, overlap. Modeling, SDBMS data model. DBMS data model must be extended by SDTs at the level of atomic data types, such as integer, string, or better be open for user-defined types, or DBMS approach. Relation states: sname, string, area, region, spop, integer. Relation cities: cname, string, center, point, extent, region, cpop, integer. Relation rivers: rname, string, route, line. Querying. The problem of querying is to connect the operations of a spatial algebra to the facilities of a DBMS query language. Spatial data require a graphical presentation of results as well as graphical input of queries, or at least SDT values used in queries. Two main issues: connecting the operations of a spatial algebra, including predicates for spatial relationships, to the facilities of a DBMS query language. Fundamental spatial algebra operator are spatial selection, spatial join, overlay, fusion. 2. Providing graphical presentation of spatial data, that is, results of queries, and graphical input of SDT values used in queries. Fundamental operations, algebra. We now consider from an algebraic point of view operations for manipulating sets of database objects with spatial attributes. They can be classified as spatial selection, Spatial Join, Spatial Function Application, other set of operations. Spatial Selection. A selection is an operation that returns from a set of objects those fulfilling a predicate. The term is used to describe a selection based on spatial predicate. Examples: find all cities in Bavaria. Select S name from cities C, where C.center inside Bavaria.area. Find all rivers intersecting a query window. Select star from rivers R, where R.root intersects window. Find all big cities no more than 100 kilometers from Hagen. Select C name from cities C, where dist C.center, Hagen.center is less than 100 kilometers and C.pop is greater than 500 kilometers. Spatial Join. Similarly to a spatial selection, a spatial join is a join which compares any two objects through a predicate on their spatial attribute values. Some examples: for each river passing through Bavaria, find all cities within less than 50 kilometers. Select R.name, C.name, length, intersection, R.root, C.area from rivers R, cities C, where R.root intersects Bavaria.area and dist R.root, C.area is less than 50. Spatial function application. In a set-oriented query, a new SDT value is computed for each object in a set. Various object algebra operators allow such an embedding of a function application. The extend operator takes an expression to be evaluated for each object and a new attribute name. It appends the resulting values as a new attribute to the object. For example, for each river going through Bavaria, return the name, the part of its geometry lying inside Bavaria, and the length of that part. River select, root intersects Bavaria, extend, intersection, root Bavaria, part, extend, length, part, p length, project, r name, part, p length. Other set operations. Such operations manipulate whole sets of spatial objects in a special way. They lie at the interface between a spatial algebra and the DBMS object algebra. Some suggested operations are the following. Overlay computes the elementary regions resulting from overlaying two partitions. It can be viewed as a special kind of spatial join. Fusion. This is a special kind of grouping. Objects are grouped by some arbitrary attribute values. For each resulting group of objects, the union of all values of a spatial attribute is formed. For example, given a set of region objects with a land use attribute, one can group by land use to obtain one object for land use wheat with the associated union region, etc. Voronoi computes from a set S of point objects a corresponding set of region objects, the Voronoi diagram. For each point P, the region consists of the points of the plane closer to P than to any other point in S. Querying, graphical input and output. Traditional database systems deal with alphanumeric data types whose values can easily be entered through a keyboard and represented textually within a query result. For example, a table. For a spatial database system, at least when it is to be used interactively, graphical presentation of SDT values in query results is essential, and entering SDT values to be used as constants in queries via a graphical input device is also important. Besides graphical representation of SDT values, another distinctive characteristic of querying a spatial database is that the goal of querying is in general to obtain a tailored picture of the space represented in the database, which means that the information to be retrieved is often not the result of a single query, but rather a combination of several queries. For example, for GIS applications, the user wants to see a map built by overlaying graphically the results of several queries. Requirements for spatial querying. Spatial data types, graphical display of query results, Graphical combination, overlay of several query results. It should be possible to start a new picture, to add a layer, or to remove a layer from the current display. Display of context. To interpret the result of a query, it is necessary to show some background, such as the boundary of a state containing it. A facility for checking the content of a display. When a picture, a map, has been composed by several queries, one should be able to check which queries have built it. Extended dialog. It should be possible to use pointing devices to select objects within a picture or sub-areas, zooming in, for example by dragging a rectangle over the picture. Varying graphical representations. It should be possible to assign different graphical representations to different object classes in a picture, or even to distinguish objects within one class. A legend should explain the assignment of graphical representations to object classes. Label placement. It should be possible to select object attributes to be used as labels within a graphical representation. Scale selection. The scale determines not only the size of the graphical representation, but possibly also what kind of symbol is used or whether an object is shown at all. Sub-area for queries. It should be possible to restrict attention to a particular area of the space for several following queries. Spatial querying requirements can in general be fulfilled by offering textual commands in the query language or within the design of a graphical user interface (GUI). A GUI will probably have at least 3 sub-windows. A text window for displaying the textual representation of a collection of objects, containing for each object its alphanumeric attributes. A graphics window containing the overlay of the graphical representations of spatial attributes of several object classes or query results, and a text window for entering queries and perhaps displaying system messages. A query consists of 3 parts. Describing the set of objects to be retrieved, as in traditional querying, partitioning the query result into subsets to be displayed in different formats by a number of display queries, describing for each subset how to render its spatial attributes. Integrating geometry into query language. Integrating geometry into a query language has the following 3 main aspects: denoting SDT values as constants in a query and graphical input of such constants, expressing the 4 classes of fundamental operations for an embedded spatial algebra, describing the presentation of results. Denoting SDT values, graphical input. In traditional query languages, constants in queries belong to an alphanumeric data type and are therefore textually representable. That is, one can simply be entered through the keyboard. This is not feasible for SDT constants. Such a constant may be entered through a graphical input device, or it could also be computed in a previous query. Object-oriented query languages usually allow one to identify one single object. One can then denote any attribute value by dot notation. For example, determine an object Bavaria and then refer to Bavaria.area. Expressing the 4 classes of fundamental operations. Spatial function application, although not possible in classical relational algebra, is also in practice provided by query languages. Describing the presentation of results. A presentation language needs some embedded general querying capabilities to determine subsets of answers to be shown in specific formats. Data structures and algorithms. Implementation of spatial algebra in an integrated manner with the DBMS query processing. Not just simply implementing atomic operations using computational geometry algorithms, but consider the use of the predicates within set-oriented query processing, spatial indexing or access methods, and spatial join algorithms. Data structures. Representation of value of a SDT must be compatible with 2 different views. DBMS perspective. Same as attribute values of other types with respect to generic operations. Can have varying and possibly large size. Reside permanently on disk pages. can efficiently be loaded into memory, offers a number of type-specific implementations for generic operations needed by the DBMS. For example, transformation functions from to ASCII or graphic. Spatial algebra implementation perspective, the representation is a value of some programming language data type, is some arbitrary data structure which is possibly quite complex, supports efficient computational geometry algorithms for spatial algebra operations, is not geared only to one particular algorithm but is balanced to support many operations well enough. From both perspectives, the representation should be mapped by the compiler into a single or perhaps a few contiguous areas to support DBMS paging. Also supports plane sweep sequence. Algorithms on the exact geometry use a plane sweep. The sweep needs the components of the object, for example, the vertices in some fixed order, for example, X order. It is highly advantageous to store this order explicitly in the object so that not every sweep needs to sort vertices first. Approximations. The implementation of many operations starts with a rough test on an approximation of the object. Usually this is the bounding box, but there can also be other approximations. Hence, these should be part of the representation. Stored unary function values. Some operations of the spatial algebra compute properties of a spatial value, for example, the area or perimeter of a region. Since these can be expensive to compute, they may be computed once after creation of the value and then stored with it. Spatial indexing. To expedite the spatial selection as well as other operations such as spatial joins, etc., it organizes space and the objects in it in some way so that only parts of the objects need to be considered to answer a query. Two main approaches. Dedicated spatial data structures, for example, R-tree. Spatial objects map to a 1D space to utilize standard indexing techniques, for example, B-tree. Spatial data structures either store points or rectangles for line or region values. Operations on those structures: insert, delete, member. Query types for points: range query, all points within a query rectangle; nearest neighbor, point closest to a query point; distance scan, enumerate points in increasing distance from a query point. Query type for rectangles: intersection query, containment query. A fundamental idea: use of approximations as keys. Continuous, for example, bounding box. Grid, a geometric entity as a set of cells. Filter and refine strategy for query processing. Filter returns a set of candidate objects which is a superset of the objects fulfilling a predicate. Refine, for each candidate the exact geometry is checked. Memory organization. A spatial index structure organizes points into buckets. Each bucket has an associated bucket region, a part of space containing all objects stored in that bucket. For point data structures, the regions are disjoint and partition space so that each point belongs into precisely one bucket. For rectangle data structures, bucket regions may overlap. One-dimensional embedding of grid approximations. The basic idea for this is to find a linear order for the cells of the grid such that cells close together in space are also close to each other in the linear order, and to define this order recursively for a grid that is obtained by a hierarchical subdivision of space. Any shape approximated as a set of cells over the grid can now be decomposed into a minimal number of cells at different levels, using always the highest possible level. Hence, for each spatial object, we can obtain a set of spatial keys. Index can be a B-tree of lexicographical ordered list of the union of these spatial keys. Spatial indexing, 2D points. Data structures representing points have a much longer tradition. KD tree and its extensions, KDB tree and LSD tree. Grid file, organizing buckets into an irregular grid of pointers. 2D rectangles. Spatial index structures for rectangles. Unlike points, rectangles don't fall into a unique cell of a partition and might intersect partition boundaries. Transformation approach. Instead of k-dimensional rectangles, 2k-dimensional points are stored using a point data structure. Overlapping regions. Partitioning a space is abandoned and bucket regions may overlap, for example, R3 and R star tree. Clipping. Keep partitioning. A rectangle that intersects partition boundaries is clipped and represented within each intersecting cell, for example, R plus tree. Spatial join. Traditional join methods such as hash join or sort or merge join are not applicable. Filtering Cartesian product is expensive. Two general classes: grid approximation, bounding box. None, one, both operands are presented in a spatial index structure. Grid approximations and overlap predicate. A parallel scan of two sets of Z elements corresponding to two sets of spatial objects is performed. Too fine a grid, too many Z elements per object, inefficient. Too coarse a grid, too many false hits in spatial join. Bounding boxes. For two sets of rectangles R, S, all pairs are S in R in capital R and S in capital S such that R intersects S. No spatial index on R and S. BB join, which uses a computational geometry algorithm to detect rectangle intersection, similar to external merge sorting. Spatial index on either R or S. Index join scan the non-indexed operand, and for each object, the bounding box of its SDT attribute is used as a search argument on the indexed operand. Only efficient if non-indexed operand is not too big, or else BB join might be better. Both R and S are indexed. Synchronize traversal of both structures so that pairs of cells of their respective partitions covering the same part of space are encountered together. System architecture. Extensions required to a standard DBMS architecture. Representations for the data types of a spatial algebra. Procedures for the atomic operations, for example, overlap. Spatial index structures. Access operations for spatial indices, for example, insert. Filter and refine techniques. Spatial join algorithms. Cost functions for all these operations. For query optimizer. Statistics for estimating selectivity of spatial selection and join. Extensions of optimizer to map queries into the specialized query processing method. Spatial data types and operations within data definition and query language. User interface extensions to handle graphical representation and input of SDT values. The only clean way to accommodate these extensions is an integrated architecture based on the use of an extendable DBMS. There is no difference in principle between a standard data type such as string and a spatial data type such as region. Same for operations, concatenating two strings or forming intersection of two regions. Clustering and secondary index for standard attribute, for example B tree, and for spatial attribute R tree. Sort, merge, join and bounding box, join query optimization, only reflected in the cost functions. GIS architectures using a closed DBMS. The two main approaches are layered architecture and dual architecture. Layered architecture. Here spatial functionality is implemented on top of a given DBMS, often a commercially available relational system. For the representation of SDT values, there are two possible strategies. The first is to let each tuple represent the coordinates of one point or line segment and to break the SDT value into pieces. The disadvantage is that for the implementation of SDT operations in the top layer, the SDT values have first to be reconstructed, which is far too expensive. The second possibility is to represent SDT values in long fields of the DBMS. This is better than breaking SDT values into pieces. It is still problematic because the DBMS handles the geometries only in the form of uninterrupted byte strings. Evaluation of any predicate or operation on an exact geometry can only be done in the top layer. Some limited form of spatial indexing can be provided by maintaining sets of Z elements for the geometries in special relations, which in turn can be indexed through a B tree. Figure shows layered architecture. Dual architecture. Here a top layer integrates two rather independent subsystems, the DBMS, which handles non-spatial data, and a spatial subsystem storing and manipulating geometries. The first part contains the non-spatial attributes and is stored in the DBMS. The second part is the spatial attribute and is kept in data structures implemented directly on top of the file system. The two pieces are connected by logical pointers. An advantage is that one is free to use adequate representations of SDT values as well as efficient data structures and algorithms for indexing and query processing within the spatial subsystem. A problem is that a query now has to be decomposed into a non-spatial part and a spatial part to be handled by the DBMS and the spatial subsystem respectively. Figure shows a dual architecture of integration layer, standard DBMS, and spatial subsystem. Text databases. A substantial portion of the available information is stored in text databases or document databases, which consist of large collections of documents from various sources such as news articles, research papers, books, digital libraries, email messages, and web pages. Text databases are rapidly growing due to the increasing amount of information available in electronic forms such as electronic publications, email, CD-ROMs, and the World Wide Web. Data stored in most text databases are semi-structured data in that they are neither completely unstructured nor completely structured. Text data analysis and information retrieval. Information retrieval is a field that has been developing in parallel with database systems for many years. Unlike the field of database systems, which has focused on query and transaction processing of structured data, information retrieval is concerned with the organization and retrieval of information from a large number of text-based documents. A typical information retrieval problem is to locate relevant documents based on user input, such as keywords or example documents. Typical information retrieval systems include online library catalog systems and online document management systems. Since information retrieval and database systems each handle different kinds of data, there are some database system problems that are usually not present in information retrieval systems, such as concurrency control, recovery, transaction management, and update unstructured documents, approximate search based on keywords, and the notion of relevance. Basle measures for text retrieval. The set of documents relevant to a query be denoted as relevant, and the set of documents retrieved be denoted as retrieved. There are two basic measures for assessing the quality of text retrieval. Precision. This is the percentage of retrieved documents that are in fact relevant to the query, correct responses. It is formally defined as precision equal to modulus of relevant intersect retrieved over modulus of retrieved. Recall. This is the percentage of documents that are relevant to the query and were in fact retrieved. It is formally defined as recall equal to modulus of relevant intersect retrieved over modulus of retrieved. Keyword-based and similarity-based retrieval. Most information retrieval systems support keyword-based and/or similarity-based retrieval. In keyword-based information retrieval, a document is represented by a string which can be identified by a set of keywords. A user provides a keyword or an expression formed out of a set of keywords such as car and repair shops, tea or coffee, or database systems, but not Oracle. A good information retrieval system should consider synonyms when answering such queries. For example, given the keyword car, synonyms such as automobile and vehicle should be considered in the search as well. Keyword-based retrieval is a simple model that can encounter two major difficulties. The first is the synonymy problem. A keyword such as software product may not appear anywhere in the document, even though the document is closely related to software product. The second is the polysemy problem. The same keyword, such as mining, may mean different things in different contexts. Similarity-based retrieval finds similar documents based on a set of common keywords. The output of such retrieval should be based on the degree of relevance, where relevance is measured based on the closeness of the keywords, the relative frequency of the keywords, and so on. It is difficult to provide a precise measure of the degree of relevance between a set of keywords, such as the distance between data mining and data analysis. A text retrieval system often associates a stop list with a set of documents. A stop list is a set of words that are deemed irrelevant. For example, a, the, of, for, with, and so on are stop words even though they may appear frequently. Stop lists may vary when the document set varies. For example, database systems could be an important keyword in a newspaper. However, it may be considered as a stop word in a set of research papers presented in a database systems conference. A group of different words may share the same word, stem. A text retrieval system needs to identify groups of words where the words in a group are small syntactic variants of one another and collect only the common word, stem, per group. For example, the group of words drug, drugged, and drugs share a common word, stem, drug, and can be viewed as different occurrences of the same word. Other text retrieval indexing techniques. There are several other popularly adopted text retrieval indexing techniques, including inverted indices and signature files. An inverted index is an index structure that maintains two hash-indexed or B+tree index tables, document table and term table, where document table consists of a set of documents record, each containing two fields, doc ID and posting list, where posting list is a list of terms or pointers to terms that occur in the document sorted according to some relevance measure. Term table consists of a set of term records, each containing two fields, term ID. Here, posting list specifies a list of document identifiers in which the term appears. A signature file is a file that stores the signature record for each document in the database. Each signature has a fixed size of B bits representing terms. A simple encoding scheme goes as follows. Each bit of document signatures is initialized to 0. A bit is set to 1 if the term it represents appears in the document. A signature S1 matches another signature S2 if each bit that is set in signature S2 is also set in S1. Since there are usually more terms than available bits, there may be multiple terms mapped into the same bit. Such multiple to one mappings make the search expensive, since a document that matches the signature of a query does not necessarily contain the set of keywords of the query. The document has to be retrieved, parsed, stemmed, and checked. Improvements can be made first by performing frequency analysis, stemming, and by filtering stop words, and then using a hashing technique and superimposed coding technique to encode the list of terms into bit representation. Text mining, keyword-based association and document classification. Keyword-based association analysis. Keyword-based association analysis collects sets of keywords or terms that occur frequently together and then finds the association or correlation relationships among them. Like most of the analyses in text databases, association analysis pre-processes the text data by parsing, stemming, removing stop words, and so on, and then evokes association mining algorithms. In a document database, each document can be viewed as a transaction, while a set of keywords in the document can be considered as a set of items in the transaction. That is, the database is in the format document ID, a set of keywords. The problem of keyword association mining in document databases is thereby mapped to item association mining in transaction databases, where many interesting methods have been developed. A set of frequently occurring consecutive or closely located keywords may form a term or a phrase. The association mining process can help detect compound associations, that is, domain-dependent terms or phrases, or non-compound associations. Mining based on these associations is referred to as term-level association mining, as opposed to mining on individual words. Term recognition and term-level association mining enjoy two advantages in text analysis. Terms and phrases are automatically tagged so that there is no need for human effort in tagging documents, and 2. The number of meaningless results greatly reduces, as is the execution time of the mining algorithms. With such term and phrase recognition, term-level mining can be evoked to find associations among a set of detected terms and keywords. Some users may like to find associations between pairs of keywords or terms from a given set of keywords or phrases, whereas others may wish to find the maximum set of terms occurring together. Therefore, based on user mining requirements, standard association mining or max pattern mining algorithms may be evoked. Document classification analysis. Automated document classification is an important text mining task, since with the existence of tremendous number of online documents, it is tedious yet essential to be able to automatically organize such documents into classes so as to facilitate document retrieval and subsequent analysis. A general procedure for performing document classification is as follows. A set of pre-classified documents is taken as a training set. The training set is then analyzed in order to derive a classification scheme. Such a classification scheme often needs to be refined with the testing process. The so-derived classification scheme can be used for classification of other online documents. This process appears similar to the classification of relational data. Relational data are well structured. Each tuple is defined by a set of attribute-value pairs. Document databases are not structured according to attribute-value pairs. That is, a set of keywords associated with a set of documents is not organized into a fixed set of attributes or dimensions. Therefore, commonly used relational data-oriented classification methods, such as decision tree analysis, cannot be used to classify document databases. An effective method for document classification is to explore association-based classification, which classifies documents based on a set of associated, frequently occurring text patterns. Association-based classification method proceeds as follows. Keywords and terms can be extracted by information retrieval and simple association analysis techniques. Concept hierarchies of keywords and terms can be obtained using available term class, such as WordNet, or relying on expert knowledge or some keyword classification systems. Documents in the training set can also be classified into class hierarchies. A term association mining method can then be applied to discover a set of associated terms that can be used to maximally distinguish one class of documents from others. This derives a set of association rules associated with each document class. Such classification rules can be ordered based on their occurrence frequency and discriminative power and used to classify new documents. Such a kind of association-based documents classifier has been proven to be effective. Time series databases. Time series DBMS. A time series DBMS is a database management system that is optimized for handling time series data. Each entry, sometimes also called an event, has an associated time stamp. Time series DBMS are designed to efficiently collect, store, and query various time series with high transaction volumes. Although time series data can be managed with other categories of DBMS, the specific challenges often require specialized systems. For example, a query like select sensor 1, CPU, frequency, sensor 2, heat, joins two time series based on the overlapping areas of time for each and outputs a single composite time series. Sources for time series data, for example, measurements generated by sensors, status information and other metrics produced from complex systems for monitoring purposes, stock tickers of high-frequency stock trading system. Industrial fleets, trucks, ships, trains, aircraft, produce location, velocity, and other operational metrics. Calls, messages, and other signals sent from communication devices or respective applications. Features of time series DBMS. Time series DBMS are designed to efficiently collect, store, and query time series data with high transaction volumes. Although that type of data could be managed with other categories of DBMS, and some systems even provide appropriate design patterns or even extensions for handling time series, the specific challenges often benefit from specialized systems by supporting downsampling data. For example, a sensor's value is stored per second and a query shall deliver the averaged value per minute. A typical SQL query needs a group by clause with an expression similar to something like group by integer division, time, 60, whereas time series DBMS support something like group by time, 1 minute. Comparison with the previous record. For example, a table contains stock prices, 1 tick per day. A query should deliver all days in which the price of a specific stock had increased. In a relational system and using standard SQL, we would have to self-join the table and figure out how to match each record with its previous one. That may be a non-trivial task and is definitely not efficient. Time series DBMS typically offers specific features for that requirement. Joining time series. Joins will put two or more time series together by matching timestamps. Those timestamps, however, may not match exactly. Time series DBMS often provide features for that task. Example, by allowing the following SQL-like syntax. Select errors per minute dot value per page views per minute dot value from errors per minute inner join page views per minute. Time series properties. Time series data are generally written in a predefined order. Time series data may be read in the predefined order or some aggregated consequence based on the need of the user. This means access to data is usually alongside the time dimension, as for instance in the retrieval of all observations over a range of consecutive dates. Consequently, storage, retrieval, and update of time series data are not independent of each other. Time series data are not commonly altered. One example of time series data is the hourly reading of a thermometer. The data are recorded in predefined intervals and are not normally modified once recorded. The data may be aggregated, but that aggregation is linked to a predefined sequential order and granularity. Time series data values are tightly associated with a predefined specific pattern of time referred to as calendar. A calendar defines a method of measurement. Within a calendar is a set of valid occurrences for which time series can be recorded. Thus, a calendar is used to determine when and how often observations are recorded. Time series data are usually manipulated as one single object, that is, as a collection of data. In other words, manipulation of data puts more emphasis on aggregation operations on collections of data rather than on an individual data item. Time series have a header, that is, a general description. The header contains all the metadata about the time series. Metadata can be information which allows the time series to be self-describing. The metadata can be information such as name, title, source, type of value, and type of time series. Classification of time series. There are two major classes of time series data, regular and irregular. These are defined by the duration between the timestamps of their elements. All regular time series have a predictable number of units between them, whereas irregular time series do not. Time series can be further classified as univariate or multivariate. Univariate time series. A time series is a collection of observations made sequentially over time. It contains a sequence of events. An event is an ordered pair consisting of temporal value and an associated list of metadata attributes, also known as header or general description. A typical time series has the following format: T1, data value 1, T2, data value 2, and so on until Tn, data value n. For I equals 1, 2 going up to n, where data value is the data value for the corresponding time, Ti. Multivariate time series. Most economic and financial information is structured in the form of multivariate time series. So changes in one element in the observations vector of one variable imply corresponding changes in other variables that belong to the phenomenon under study. Therefore, many time series have multiple values instead of a single value. These time series are known as multivariate time series. They generally have the following format: T1, T2 up to Tn. Figure shows a time series classification. Challenges in time series data management. Mapping time series data to relational database. Formal definition of time series dimensions. On the need for a time series grouping mechanism. Framework for time series data management. Web mining. Web mining is the application of data mining techniques to extract knowledge from the web data, that is, web content, web structure, and web usage data. Web mining can be broadly divided into three distinct categories: web content mining, web structure mining, web usage mining. The figure shows web mining taxonomy. Web mining, web content mining. Web content mining. Web content mining is the process of extracting useful information from the contents of web documents. Content data is a collection of facts a web page is designed to contain. It may consist of text, images, audio, video, or structured records such as lists and tables. Application of text mining to web content has been the most widely researched. Issues addressed in text mining include topic discovery and tracking, extracting association patterns, clustering of web documents, and classification of web pages. Research activities on this topic have drawn heavily on techniques developed in other disciplines such as information retrieval (IR) and natural language processing (NLP). While there exists a significant body of work in extracting knowledge from images in the fields of image processing and computer vision, the application of these techniques to web content mining has been limited. Pre-processing content. Content preparation. Extract text from HTML. Perform stemming. Remove stop words. Calculate collection wide word frequencies (DF). Calculate per document term frequencies (TF). Vector creation. Common information retrieval technique. Each document HTML page is represented by a sparse vector of term weights. TF-IDF weighting is most common. Typically, additional weight is given to terms appearing as keywords or in titles. Common mining techniques. The more basic and popular data mining techniques include classification, clustering, associations. The other significant ideas: topic identification, tracking, and drift analysis, concept hierarchy creation, relevance of content. Document classification. Supervised technique. Categories are defined and documents are assigned to one or more existing categories. The definition of a category is usually in the form of a term vector that is produced during a training phase. Training is performed through the use of documents that have already been classified, often by hand, as belonging to a category. Document clustering. Unsupervised technique. Documents are divided into groups based on similarity metric. No predefined notion of what the groups should be. Most common similarity metric is the dot product between two document vectors. Topic identification and tracking. Combination of clustering and classification. As new documents are added to a collection, an attempt is made to assign each document to an existing topic category. The collection is also checked for the emergence of new topics. The drift in the topics are also identified. Concept hierarchy creation. Creation of concept hierarchies is important to understand the category and subcategories a document belongs to. Key factors. Organization of categories, for example, flat, tree, or network. Maximum number of categories per document. Category dimensions, for example, subject, location, time, alphabetical, numerical. Relevance of content. Relevance can be measured with respect to any of the following criteria: document, query-based, user-based, role or task-based. Document relevance. Measure of how useful a given document is in a given situation. Commonly seen in the context of queries, results are ordered by some measure of relevance. In general, a query is not necessary to assign a relevance score to a document. Query-based relevance. Most common, well established in information retrieval. Similarity between query keywords and document is calculated. Can be enhanced through additional information such as popularity in Google or term positions in Alta Vista. User-based relevance. Often associated with personalization. Profile for a particular user is created. Z similarity between a profile and document is calculated. No query is necessary. Role or task-based relevance. Similar to user-based relevance, profile is based on a particular role or task instead of an individual. Input to profile can come from multiple users. Web content mining applications. Identify the topics represented by web documents. Categorize web documents. Find web pages across different servers that are similar. Applications related to relevance. Queries. Enhance standard query relevance with user, role, and/or task-based relevance. Recommendations. List of top-end relevant documents in a collection or portion of a collection. Filters. Show or hide documents based on relevance scores. Web mining. Web usage mining. A web is a collection of interrelated files on one or more web servers. Web usage mining discovery of meaningful patterns from data generated by client-server transactions on one or more web localities. Typical sources of data. Automatically generated data stored in server access logs, referrer logs, agent logs, and client-side cookies. User profiles, metadata, page attributes, content attributes, usage data. Figure shows web usage mining process. Figure shows the pre-processing architecture. Classification of web usage mining. Web server data. User logs are collected by the web server and typically include IP address, page reference, and access time. Application server data. Commercial application servers such as WebLogic 1, 2, Story Server 3 have significant features to enable e-commerce applications to be built on top of them with little effort. A key feature is the ability to track various kinds of business events and log them in application server logs. Application level data. New kinds of events can be defined in an application and logging can be turned on for them, generating histories of these events. Implications of web usage mining for e-commerce. Determine lifetime value of clients. Design cross-marketing strategies across products. Evaluate promotional campaigns. Target electronic ads and coupons at user groups based on their access patterns. Predict user behavior based on previously learned rules and users' profile. Present dynamic information to users based on their interests and profiles. Implications for other applications. Effective and efficient web presence. Determine the best way to structure the website. Identify weak links for elimination or enhancement. As site-specific web design agent, prefetch files that are most likely to be accessed. Intra-organizational applications. Enhance workgroup management and communication. Evaluate intranet effectiveness and identify structural needs and requirements. Web mining, weblog attribute. Mining weblogs. To mine knowledge from the weblogs, we use two data mining techniques: clustering, association rules generation. Before mining, information from the log sessions from the logs are created. Session generation. Since web servers do not typically log usernames, this technique defines a user session or as accesses from the same IP address such that the duration of time elapsed between two consecutive accesses in the session is within a pre-specified threshold. This distinguishes it from other approaches which assume that a user's identity is known. Each URL in the site is assigned a unique number. J belongs to the set 1 up to modulus U, where modulus U is the total number of valid URLs. The ith user session is encoded as a modulus U dimensional binary attribute vector I, S with the property Sj to the power of I equals 1 if user accessed the jth URL in the ith session, 0 otherwise. This schema will match one's user sessions into multiple user sessions. Majority of a user's sessions follow a similar pattern, then clearly no difference is made. If the same user displays a few different access patterns on a site, this notion of a multiple user sessions enables one to capture this behavior. Association rules. To generate the association rules for the weblogs, we first generated the sessions and URL files. Mindset requires two input files for generating the association rules, a schema file and a data file. The schema file describes the structure fields of the data file. The data file consisted of the binary sessions vector. Each session can be thought of as a transaction and each URL as an item in the association rule context. Thus, a session 10110 would imply that URLs 1, 3, and 4 were visited in the session and URLs 2 and 5 were not. This schema file was simply the URL numbers and was generated using a Perl program. The association file generated by Mindset was cleaned before the result could be analyzed. Clustering. Since sessions are not object data, a distance measure is not automatically available. Consider two user sessions, SK and SM. First, consider the case where URLs accessed in the sessions are considered independent of the structure of the site. Then the cosine of the angle between SK and SL, called M1, is a measure of similarity. M1 simply measures the number of identical URLs accessed during the two sessions relative to the number of URLs accessed in both sessions and completely ignores the hierarchical organization of the website. This adversely affects its ability to capture correct profiles. Another similarity measure takes into account the site structure. The website is modeled as a tree, essentially the directory structure rooted at the server's document root, with links such as redirects and aliases explicitly brought in. Taking into account the syntactic representation of two URLs, their similarity is assessed by comparing the location of the corresponding nodes on the tree. This is done by comparing the paths from the root of the tree to the two nodes. The syntactic similarity between the ith and jth URLs is shown on the screen, where pi denotes the path traversed from the root node to the node corresponding to the ith URL, and modulus pi indicates the length of this path or the number of edges included in the path. This similarity, which lies in 0, 1, measures the amount of overlap between the paths of the two URLs. Given this similarity between URLs, a new similarity measure between sessions is defined as shown on the screen. Due to similarity underestimation by both M1 and M2 in specific cases, they propose M equals max of M1, M2 as a similarity measure. This similarity is mapped to the dissimilarity measure D equals 1 minus M squared, the whole squared. Evaluating the results. We interpret the results of applying the clustering algorithm on the user session data by using the following quantitative measures. The clustering algorithm assigns user sessions to the closest clusters based on the similarity measures. This creates C clusters Xi equals the set S power k belongs to S, such that dik is less than djk for all j not equal to I for I lying between 1 and C. The sessions in cluster Xi are summarized in a typical session profile vector Pi equals Pi1 going up to Pi modulus of u, the whole raised to the power t. The components of Pi represent the degree with which each URL belongs to a session. This is computed as Dij equal to P of Sj of k equal to 1, such that S of k belongs to Xi equals modulus of Xij over modulus of Xi, where Xij equals the set S of k belongs to Xi such that Sj of k is greater than 0. In other words, it measures the fraction of the clusters in the session which included this URL. This helps us recognize those URLs which form the core of the profile. For some URLs, the degree is greater than 1. This is because we group together all the URLs that belong to the same directory. Besides summarizing profiles, the components of the profile vector can be used to recognize an invalid profile which has no strong or frequent access pattern. Conclusion. In this chapter, we have covered the following in detail: data mining issues in object-oriented databases, spatial databases and multimedia databases, time series databases, text databases, web mining, web usage mining, web content mining, weblog attribute.